Myself Sindhu Rekha, Assistant Professor, Department of ECE in Mlritm Engineering College. Today I am going to discuss about the topic is built-in self-test, that is nothing but Bist. So coming to the Bist structure. So in this we can add extra hardware to the chip for generating the test patterns and response evaluation. In this we can done on the chip, and additionally we can require hardware, and another one is a few external pins to control Bist operation. One is input pin and another one is output pin. Here input pin is nothing but test control and output pin is nothing but good and bad. Here we can decide the chip is good or bad condition. And then coming to why you go for Bist operation. So for it is used for field test and diagnosis. So for this purpose, we can go for the Bist operation. So instead of Bist, we can use the ATE, means automated test equipment. So this is very cost compared to the Bist. So that's why we can go for the Bist operation instead of ATE. So and also we can do two types of tests, that is software test and then hardware test. Due to the software test, it is low hardware fault coverage and it gives poor diagnostic resolution and it takes time consuming. And coming to the hardware testing, lower system test effort and better diagnosis, and it gives improved system maintenance and repair. That's why hardware testing is good compared to the software test. And there are two types of Bist operations, that is logic Bist, means L Bist, and then second one is the memory Bist, means M Bist. So by using the logic Bist operation, it is designed for the testing random logic, and we can use PRPG, means pseudo random pattern generator. By using this we can generate the random input pattern. And also MISR means multiple input signature register. It gives response of input pattern, and MISR output indicates the defects in the device. That means it finds out the defaults in the IC or nothing but device. Coming to the memory Bist, M Bist, it is used for testing memories, and it has a circuit that apply read and compare the test patterns. So before that we can store the test patterns into the memory, that is called memory Bist. There are some industry standards for M Bist, that is SRAM and DRAM. So this is the types of Bist. And then coming to the architecture of the Bist in built-in self-test. So these many components we require to generate the Bist operation. So those are test control, pattern generator and multiplexer, and circuit under test, response compactor, and memory unit, that is nothing but ROM memory. So first of all we can enable the test control, then only the entire circuit is on condition, and here we can give the IC or device. So whatever the IC we have to test our device, we can apply that IC in this box, means circuit under test. And then test controller is one. Here test controller, this test controller controls the remaining all the components. So here we can give the inputs, means this pattern generator generate the input patterns by using the test controller. This output is given to the multiplexer. So and then here we can take the input through the multiplexer device and then give the output, and this output comes to the response compactor. Here ROM memory already stored the previous results or instant results. So here we can compare the resultant stored outputs and exact expected output. If both are same, that IC is good. If not equal, that IC is bad. Here P1, PI or PO, means PI means primary inputs and PO means primary outputs. And PI and PO are external pins. So these pins are not going to be tested. So this is the Bist architecture. And coming to the advantages of Bist, so it already we discussed it in previous. It reduced the cost compared to the ATE, and then speed and efficiency improvements, and improved the fault coverage, and then simplified the debugging concept. And then disadvantages of Bist, it occupies the more area and power overhead, means we can add additionally hardware equipment to the IC. That's why it occupies more area and power, and design complexity is also less, and poor performance, and decrease the test reliability. So these are the disadvantages of Bist. Now coming to the LFSR. Here LFSR means linear feedback shift register. This is implemented by using the field programmable gate array. So in this multiple shift registers are connected in a series manner. So that's why we can call this is serial linear feedback shift register. So in this we can use the XOR operation or XNOR operation. So output of the XNOR gate is feedback to the beginning of the shift register. So we can fed back the output of the shift register like this. Here we can place the XOR gate. So that's why this is called linear feedback shift register. See here, all shift registers, 4 shift registers are connected in series manner and then fed back to the first input. So that's why it is called linear feedback shift register. So we have 2 types of structures. Type 1. In type 1, D1, D2, D3, D4 are connected in a series manner, and output of D4 is connected to the, so this is the XOR gate. So this is XOR gate. So D4 output is given to here, and one more input is coming from D1, and this XOR output is fed back to the D1 register, that is type 1. And here coming to the type 2. So instead of D3 and D4, we can place the XOR. So depends on this, so we can get the output. Mostly we can choose the structure of LFSR is type 1. So I will explain with the example here. So I'll take the 4-bit shift register. So initially I can store the data is D1 is 0, D2 is 0, D3 is 0, and D4 is 1. Initially stored data is 0001. Now this 1 is given to the XOR. So what is the XOR gate? Truth table, ABC are the input and C is the output. Combinations are 00, 01, 10, 11. For 00, 0, for 11 it will get 0. So 01, 10 it will get 11. Okay. By using this XOR gate operation, we can get the output of LFSR. Now this 1 is coming here. This 1 is output of, what is the output of D4? This D4 output is coming here, and then here 0 is there. So 1 XOR 0. 1 XOR 0 output is 1. So here we'll get the output value is 1. This 1 is fed back to the D1 register. So now here 1 is stored in D1 register. This 0 is shifted to here, and this 0 is shifted to D3 register, and this 0 shifted to D4 register. Now D4 value will be 0. Now here value is 0, and here value is 1. 1 XOR 0. Again value will 1. So now D1 value is 1. So previous this 1 is shifted to here. So 1, 0, 0. So like this we can perform the operation up to 15 clock cycles. So after 16th clock cycle, we can get the same input. Whatever the input we can give in the initial stage 0001. So 0001 we can get after 15 cycles, we can get the same output. Why? Because 4-bit input patterns. For 4-bit we can get 2 power 4 equal to 16. So 0 to 15 clock pulses, total 16. So this is the LFSR pattern generation. So this is the structural diagram. Here we can take the sequential clock pulse. When it is 1, all the D flip-flops are enabled at a time. Why? Because this is a sequential clock. Depends on that, we can give the input and to the XOR gate and take the output and given to the first shift register. So depends on this, we can assign some polynomial equations. So these are the standard polynomial equations, means that is fixed already, implemented. So we can use directly for 3-bit equation. 3-bit for 3-bit we can take, for 3-bit the equation will be x power 3, first is bit value x power 3, and here 1 means x. So x power 1 equal to x only, right? So that's why equation will be x power 3 plus x plus 1. For 4-bit, x power 4 as it is, and then 1 means x power 1, 0 means 1. This is the polynomial equation for 4-bit. Like this, 5th bit, so x power 5, x power 2 plus 0 means 1. For 6 bits, x power 6, x plus 1. So for 7-bit, x power 7 plus x plus 1. So like this, we can use these many polynomial equations directly. And then coming to the applications of LFSR, so we can easily find out the error detection and error correction in Hamming code concept. Hamming code concept, and then generate the test patterns in built-in self-test, and then used in digital signal processing. So used in Bist also to generate the input vectors and used in data compressions. Thank you.